Log on, tune in, find out. Another good idea from Cambridge.
He made a big breakthrough of the uniqueness of the inverse conducting problem and always giving beautiful ideas of inverse problems. Today he's going to talk about transmission eigenvalues via upper triangular compact operators. Please.
Thank you, and thanks very much to everyone for the opportunity.
Could you bellow?
Oh, yes, actually.
No, it doesn't help. It's on before.
Okay, so I'll speak louder. Thank you. Okay. So what I'm going to discuss is transmission eigenvalues. You'll hear about that again tomorrow from several people. But I'm going to start by giving you a sort of very rapid motivation. Okay. So the motivation starts with scattering theory. Okay. Time harmonic waves. Okay. And waves we typically give three labels. Okay. So solutions in free space we call incident or free waves. They solve just the homogeneous Helmholtz equations. Okay. Solutions with a source we're going to call either radiating or outgoing waves. Okay. They're waves that are generated by the source, and we typically, if we're doing a PDE, in order to get a unique solution, we give a boundary condition, an asymptotic boundary condition at infinity. These describe waves that are actually produced by the source. It means that there's nobody standing there at infinity sending in energy. Okay? And when we have a perturbed medium, 1 plus m is the square of the index of refraction. Okay? I'll refer to that solution in all space as a total wave, and I'll often refer to the function m of x as the scatterer. It's the perturbation that causes a scattered wave. Okay? For the most part, I won't say a lot about the spaces in which these solutions exist. There are issues that have been resolved for quite some time because local L2 behavior and behavior at infinity are different. And typically, we take a source that's in a weighted L2 space, and we get solutions that are in another weighted L2 space with exactly the opposite weight. And a more accurate description is often given in terms of some Besov spaces, which I won't quite define. They're L2 norms on dyadic rings. And I guess the feature that's persistent in every case is that sources and waves always are dual to one another. There's sort of a natural duality, and you see that no matter how you try to prove estimates, you'll always wind up being able to estimate the solution in a norm that's dual to the norm in which you're estimating the source. Okay. So an elementary version of the scattering operator is, it's the map, I'm going to call it S, that takes incident waves to scattered waves. And when I talk about the scattered wave, I mean the scattered wave outside the support of the scatterer. So if the scatterer was supported in here, then I'm thinking about the scattered wave, the wave that's actually radiated outside the place where I have the scatterer. Okay. And the sort of typical thing you need to show to have a scattering theory is that you have existence and uniqueness. Okay? And so the statements I have up here simply say that every total wave can be uniquely decomposed as an incident wave plus a scattered wave. Okay? In some sense, that's a completeness statement. And you can choose, for every incident wave you choose, there's a unique total wave and a scattered wave. Okay? And from that point of view, proving these things is pretty straightforward. If you start with a UM, a total wave, you simply solve the source problem. Here's a source, find U plus, then the incident wave, you check that the difference is an incident wave. Okay? And the B could be proved in the same way. So it's fairly straightforward. Okay? We could give a more accurate description of scattering in terms of asymptotics at infinity, but in this case I choose not to. So I'm going to talk about S as the scattering operator. I could associate the asymptotics of V0 with the asymptotics of U plus but essentially I'd still be talking about the same operator. Okay. So one way to arrive at the so-called transmission eigenvalue problem is to simply ask, is the scattering operator one-to-one? Okay. And if it is, or if I should say, if it's not, then some V0 will be mapped to a U plus that's in fact identically 0 outside the domain. And in particular, that'll mean that it's Cauchy data. Its restriction to the boundary, so I'm calling the domain D, and the restriction of its normal derivative to the boundary will also be 0. Okay? So that's the statement of what I'll call the interior transmission eigenvalue problem. Okay? So the scattered wave satisfies this equation. Again, if I called this the total wave and put a 0 in here and expanded, I just did some algebra to get to that part. Okay. And the incident wave satisfies the homogeneous equation. Okay. And at a transmission eigenvalue, the scattered wave has Cauchy data 0 on the boundary. Okay. Since I'm now talking about a problem in a domain, I'm going to erase a few things. So first of all, I'll no longer distinguish between outgoing and incident waves. I'll just call these U and V because we're inside the domain. And for convenience, I'm also going to erase k squared. I can do that because I can simply rescale V. I can change V to V over k squared. And the thing to note is, if I found one of these interior transmission eigenvalues and I want to relate it back to the scattering problem, extending the U, well, this guy still has the plus that I should have erased, is straightforward because since it has 0 Cauchy data on the boundary, you can extend it to be 0 outside, and anything that's 0 is radiating. It satisfies the radiation condition. Okay. The one place where the association is no longer quite clear is what about the incident wave? When we find a problem in this region, it's not clear that the incident wave will extend to Rn. In many cases, my best guess is that it won't. But it is in some sense approximated by such things. Okay, so background. The motivation, or I should say the problem originally arose in connection with linear sampling and factorization methods. And I'm paraphrasing the question about whether it's one-to-one, just saying that do all incident waves scatter? Okay? And the dual way to pose that question are all scattered far field, are scattered far fields dense? Among all possible far fields that one could obtain, say, from sources, are the ones scattered by the scatterer M dense? These two questions turn out to be equivalent, but I haven't really explained that. If we were doing obstacle scattering, the answer would be yes to both of these questions as long as k squared was not a Dirichlet eigenvalue. In the case of a penetrable medium, a scatterer M, almost by definition, the answer is yes if k squared is not a transmission eigenvalue. Okay, so transmission eigenvalues are an analog to Dirichlet eigenvalues, and we might expect some similarities. Problem was first introduced by Colton and Monk in '88, and in 1989, Colton, Kirsch, and Pivarinta showed that they are at most discrete. Okay. And then Lassi, Pivarinta, and I, 20 years later, showed that in fact for general domains they exist under the hypothesis that M is positive, and we also had a we needed to assume that M was bigger than not just 0, but some ratio relating Dirichlet eigenvalues and clamped plate eigenvalues. But soon, Sacconi and Gentidis removed that assumption, and Sacconi and Gentidis and Hadar showed that in fact not only do some exist, but there are always infinitely many as long as M is strictly positive. Okay. And later, Sacconi, Colton, and Hadar showed that in fact you can even let M be 0 on certain interior regions. Okay. So A second proof of discreteness was given by Rinn and Sleeman in 1991. And I want to start by basically summarizing that proof because it leads to some of the methods that I'm going to describe later. So over here, you're going to follow the arrows to read this. So I've changed k squared to tau because I'm going to start thinking of it as an eigenvalue parameter. Okay. So here's the equation for the u, which was the scattered wave. Here's the equation for the incident wave. And my point of view on this is always going to be this is a system, and the only thing that makes this somewhat non-standard is the fact that u has to satisfy two boundary conditions and v doesn't have any. Okay. So Rinn and Sleeman's approach was if m is strictly positive, but v doesn't have enough boundary conditions, so what I should do is just try to eliminate v. Then I don't have to care about the fact that it doesn't have boundary conditions. So they multiplied the top equation by 1 over m. Now there's a v on the right, but now you apply this operator and the v is 0. And so now they obtained a fourth order operator with two boundary conditions for u. That's a well-posed elliptic problem. Okay? And in particular, they noticed that if you write this out, this is Laplacian 1 over m Laplacian, the principal term. I'll typically use the notation sub 0, 0 is reminding me of the boundary conditions. Okay? So 0, 0 means Dirichlet and Neumann boundary conditions. Okay? Plus the rest of the operator. Okay? So that's self-adjoint positive definite, that's invertible, and f of tau is relatively compact compared to that operator and depends on tau quadratically, tau and tau. So if you want to compute the inverse of that operator, you can do it in a standard way. You factor out the operator you know is invertible. You look at the rest, and that's identity plus compact. Okay? And because that's identity plus compact depends analytically on tau, and if you check that f of 0 is 0, when tau is 0, it's the identity, so it's invertible. And so then what we call the analytic Fredholm theorem guarantees that it's invertible on the complex plane minus a discrete set. Okay? So the conclusion is that these transmission eigenvalues are at most a discrete set. Okay? Lassi, Paivarinta, and I noticed one more thing about this fourth order equation. We noticed that if you look at this operator, if you didn't have the 1 over m in here, it's not hard to see that these two operators don't commute. But if you put the 1 over m in the middle, the fact is that they do commute. Okay, and to check that, just if you write it out, you'll see that that, at least formally, is equal to that. And because they commute, that means that when I take the adjoint, right, the adjoint of Laplacian 0, 0 is Laplacian with no boundary conditions. So when I take the adjoint, I get back the same thing. So for real values of tau, this is a self-adjoint operator. Okay. So it's self-adjoint. It's not hard to check that it's bounded below, and it in fact has a compact resolvent. Okay. T of 0, when tau is 0, is a positive definite operator. Okay. And what we showed was, so Q is the quadratic form associated to T. So I've written here the quadratic form, and I ask you to trust my algebra. Okay, and what you see are there are two positive terms. So the highest order term is positive, the lowest order term is positive, but the term in the middle is negative. Okay? And so what we showed is that there is an n-dimensional subspace of u's on which that quadratic form is negative. Okay? And we assumed that m was big enough. We now know that we don't need to assume that. Okay? And once we know that the quadratic form is negative, right, then we know that positive definite at 0, it has n negative eigenvalues at some tau, and so the eigenvalues depend continuously on the operator, but in particular on the parameter tau. So the eigenvalues must have crossed 0. Okay. When the eigenvalue crosses 0, that's what we mean by tau being a transmission eigenvalue. And maybe I should pause for a second because I've used eigenvalue twice. Okay? So initially, I was calling tau an eigenvalue, a so-called transmission eigenvalue. And I shifted on you, and I should have warned you that at this point, tau is no longer, I'm not thinking of it as an eigenvalue, it's a parameter. And I'm asking for what values of the parameter does this operator have a 0 eigenvalue? Okay, so now I'm thinking of eigenvalues as being parameterized by tau. And what this picture shows is that under the conditions, if they're all positive at 0 and there are some negative ones at some point tau, then there were taus in between where they cross 0. So Sacconi-Gentidis and Sacconi-Gentidis-Hadar improved that argument to show that, in fact, there were always infinitely many of these taus. Okay. And what they did, I'm summarizing here. So here's my domain D. Okay. And inside D, I've placed a number of balls or disks. These disks are all translates of the same disk, same radius. And I'm going to think about a quadratic form supported just on D. And I'm going to take this, on that disk, I'm going to put a constant m star that's always smaller than the m I'm interested in. Okay, and I have written here lightly that what you should notice is that this quadratic form is monotone in m. It's actually monotone decreasing in m. There are no m's don't appear here, and here you see a 1 over m. Now, the disk, if you examine the radially symmetric case, you can show in a straightforward way that the disk always has a transmission eigenvalue. So there is a lowest transmission eigenvalue for the disk. It has an eigenfunction, and if you remember, these eigenfunctions vanish to second order on the boundary. Their Cauchy data vanishes identically. Okay? So I'm going to assign to this whole region D a set of functions uj. And uj are just this eigenfunction translated to each of the disks. And if I do that, because these things are transmission eigenfunctions, the quadratic form evaluated on each of the uj's is 0. But this m is smaller than my m, and because of monotonicity, the quadratic form for the entire domain is always smaller than this one. So that means that this quadratic form is negative on the span of these functions, the uj's. Okay? And there are, if I can fit capital N disks in here, that gives me n functions uj. They're supported on disjoint sets, so they're linearly independent. So I can conclude that this is negative on an n-dimensional space. So there must be capital N real transmission eigenvalues less than or equal to that number. And if you count a little bit carefully, sort of in a way that's similar to finding a counting function for the Dirichlet eigenvalues, what you can conclude from that is that the number of eigenvalues less than or equal to tau is at least a constant that depends on m. Right? We only understand that dependence in a very few cases, roughly times the volume of the region times tau to the n over 2, which is similar to the asymptotics of counting, say, for Dirichlet eigenvalues. Okay. So I'm now going to leave the case that m is positive. Okay. And what I'm going to do is, instead of eliminating v by a fourth order equation, I want to now look directly at this 2 by 2 system. Okay? And again, the point is that u has too many boundary conditions and v has too few. Okay. I'm now no longer going to think of k squared as a parameter, but I'm going to really view it as the eigenvalue parameter. Okay. So I've just done a little bit of rearrangement. Okay, I've taken the m and put it on that side and the eigenvalue parameters and put them over here. And I want to look at this as an eigenvalue problem. So the operator B has I'm looking for eigenvalues minus k squared. Okay, so define I sub m to be the matrix that records this. And now the lambdas are the transmission eigenvalues. So I'm looking for the eigenvalues, the solutions to this generalized eigenvalue problem. B minus lambda Im applied to uv is 0. Okay. And again, the notation is this reminds me that u satisfies 2 boundary conditions, and this little line reminds me that v satisfies none. These are the operators, and so that the transmission eigenvalues are just the spectrum of I sub m inverse b. The first case I'm going to look at is what's called the Born approximation. The Born approximation is the case where m is small compared to 1. Okay, so it literally is the Frechet derivative of this problem at m equals 0, but what it amounts to doing is simply I can cross out that m because it's small compared to 1. That m stays because it's still large compared to 0. Okay. Okay, so I'm looking for, in the Born approximation, the transmission eigenvalues are the spectrum of that operator B. Okay. So B, I'll mention the domain of B, right? It's Sobolev space H20 because U satisfies 2 boundary conditions, and it's V's that are simply square integrable with square integrable Laplacian. Okay, and B maps that into L2 plus L2. Okay. So the theorem I'm going to tell you is that in the Born approximation, I'm going to assume that M is bounded, and it satisfies in a neighborhood of the boundary. So my hypothesis on M is going to be not that it's positive everywhere, but that it's positive in a neighborhood of the boundary. Okay? This is a coercivity hypothesis. It's slightly more general, but it's probably easier to think at the moment to just take the case where theta is 0. Where theta is 0, this just says that the real part of M should be bounded below in a neighborhood of the boundary. Okay? And the statement in that case is not that this operator will now have a compact resolvent, but that it will have an upper triangular compact resolvent. Okay? And what that means is that there's at least one lambda, so that B minus lambda 0I is invertible, and that inverse is an upper triangular compact operator. An upper triangular compact in this case means exactly that when I write out the inverse and I write it in as a block decomposition, that compact, 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 but the piece in the lower corner need only be bounded. Okay. And the corollary of that is going to be that the spectrum of B is discrete with finite multiplicity. And up to this point, the corollary, unfortunately, is not that it's non-empty, although I believe that should be the case. I don't know how to do that yet. And for the full problem, so I just described to you a criterion under which the spectrum of that operator was discrete. Now I'm going to go back to this generalized problem and put the M back. Okay. And the statement is similar, but not as strong. So the first, I need the hypothesis that the real part of this 1 plus m is positive. That makes sense. That's saying that this is really a Helmholtz equation. It came from a wave equation. Okay? And the second statement looks similar, but here we require that the theta be not any angle, but between minus pi over 2 and pi over 2. And the difference is, this is genuinely a positivity assumption. There's a difference here between positive and negative. Okay. And again, probably the best way to read this the first time through is simply that m is bigger than m star, bigger than 0. Okay. And in this case, if in fact m is negative, okay, if m on the boundary is negative, the same result is true, but I need to assume more, namely that m is real in the whole domain. Whether that's relevant to the problem or just a side effect of the proof, I don't know. Okay? And then the conclusion is the same one, that this IM inverse B has upper triangular compact resolvent, which means that the spectrum is discrete and has finite multiplicity. So the arguments are fairly straightforward, and I think they explain where this upper triangular compactness comes from. So I want to really describe exactly how this goes. Okay. And so I want to start by asking, what can we say about V? So here's the equation, Laplacian minus lambda V is G. V doesn't satisfy any boundary conditions. And if I want to estimate it, one thing I can do is try to estimate phi times V. And I haven't written down what phi is, but I mean phi to be just a cutoff function. So phi is a smooth positive function that is 1 in a neighborhood of the boundary. Did I say it backwards? Yes, it's 0 in a neighborhood of the boundary and becomes 1 in the interior. And then I can do, in some sense, the standard thing. I can now multiply this not by V, but by phi V, or phi squared V, and integrate by parts. And if you do that and arrange a little bit carefully, this is what you'll see. Okay, a standard estimate for a Dirichlet problem, except that there's a phi in there. Okay. Okay. Now I can take this, of course, I'm estimating this is V in the inside, but in terms of itself, so I can take this and break it into two pieces, the inside piece and the outside piece. And because I've chosen lambda to be a large positive parameter, I can absorb the inside piece over here. Okay? So I now have an estimate that says inside is bounded in terms of outside plus the forcing term. Okay. Then I can add, of course, the outside piece to both sides, and so that says that I can actually estimate the norm of V in terms of just the norm of V in the outside part. Okay. I want to estimate it in terms of M, in terms of an expression involving M, for reasons I'll show you later. Okay. So then I can observe that in this outside part, that's the place where I know M is strictly positive. It's bounded below by something. So this guy is bounded. I can always put an M in here at the cost of a different constant. Okay. And then I can go ahead and add in the integral of mv squared over the inside of D, because that's bounded from above. And so, again, at the cost of at the cost of changing the constant, I wind up with the fact that what I know from this problem is that if I can estimate M times V squared, then I can estimate the norm of V. Okay? And that's going to be the way I control the behavior of V. Okay. Okay. So I'm now going to estimate V from the equations. Again, here they are. Okay. Okay. Again, I'd like to do the standard thing, multiply by a U or a V and integrate by parts. Okay. I can't multiply this. If I multiply this equation by V and integrate by parts, I get some boundary terms that I don't know how to control. Okay. But what I can do is multiply this one by U and this one by V, okay, and use the fact that U vanishes to second order on the boundary. Okay. So a consequence of that is that if I take Laplacian minus lambda U and multiply by V, if I integrate by parts twice, that's the same as Laplacian minus lambda V times U. And that means that if I multiply this equation by V and that one by U, that after I integrate, these two terms will cancel. And what I wind up seeing is that the integral of M times V squared is given in terms of F times V and G times U. Okay. Okay. And that's the reason for the previous slide, because I now know that if I can estimate this, I can actually estimate v. So v squared is bounded by f squared and a g squared and norm g times norm u. Okay, so I have an estimate for v in terms of the right-hand sides and u. Okay, I can estimate u in the standard way. Just multiply by u bar, integrate by parts. Okay, and I wind up with an estimate that says u and its gradient are bounded by its right-hand side. And its right-hand side consists of f and v. And that's exactly what that says. So I've now put them together. Okay, and I guess I should point out that I have an estimate for u in terms of f and v, but not just of, sorry, fingers are too quick. Right. But v divided by a large parameter. I have an estimate for v in terms of u. Okay, when I put that together, because this is a large parameter, I can then move everything to the left-hand side. I probably should have said that in a clearer way. But in the end, I wind up with the following. I have estimates for v, u, and the gradient of u. And what does that tell me about the operator b? Well, certainly the kernel is empty, because again, if f and g are 0, then u and v are 0. Okay. It's fairly straightforward to check that b has closed range. I haven't checked that here. But it also tells me that the co-kernel is empty. And the reason for that is, if this is b, and you compute the adjoint of b, you'll find that the adjoint of b is the same as b, except the roles of u and v have been switched. Now it's v that satisfies two boundary conditions and u that satisfies none. And if you look carefully at my hypothesis, you'll see that if m satisfies the hypothesis, so does its complex conjugate. Okay. So the consequence is that I've now shown that b minus lambda I is actually an invertible operator. Okay. And now I can ask, now that I know it exists, I can ask, is it compact? Okay. So again, here are the estimates. These are the equations. So I can say, okay, describe it in terms of the two separate L2 spaces, and I'm just going to call the blocks R's. Well, R11 maps F's to U's. You set G equal to 0 and you forget about V. Well, right, we have estimates for U and its gradient, so that's certainly a compact operator. Right, R12 maps G's to U's. Again, we have estimates for U and its gradient, so that's also a compact operator. Okay. R21, that's the guy in the lower triangle. That's not a compact operator. And maybe the easiest way to see that, the simplest example is if you take lambda to be 0 and m to be 1, then if f is harmonic, R21 of f is just f. So if m is 1 and lambda is 0, this map is in fact the identity when you restrict it to the subspace of harmonic functions. And I've written that if we now take d to be the disk, you can check that that root n plus 1 times z to the n is an infinite dimensional family of functions of norm 1. Okay, so this operator is genuinely not compact. Okay. And R22, the thing that maps, set f equal to 0 and you map g to the v's, that is also compact, but it's not so obvious. It takes a little bit of an observation to see. So I'm going to start with an equality that this was the first integration by parts I showed you. We're in the case where f is 0, so that term's not here. Okay. If you remember, we had interior estimates. So the map from g to phi v, phi again is just a cutoff function that's 0 near the boundary. That's compact. So if I have a sequence of gn's that are going weakly to 0, the map from G to U is compact. So the UNs are going strongly to 0. The phi VNs from also compact are going strongly to 0. But the integral of m times Vn squared, that's Gn Un. These go weakly, these go strongly, so this goes to 0. Okay. And mVn squared is the outside part plus the inside part. The inside part's going to 0, so what we've now concluded is that the outside part is going to 0. That's where m is positive. That's where we have a lower bound. Okay. So the Vn's go to 0. Okay. 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 So what I claim I've just shown you is that the inverse to this operator for a large positive lambda is an upper triangular compact operator. Okay. And so now I'm going to use the resolvent identity, which is what we typically, we want to consider the inverse to b minus mu I. We know that b minus lambda naught I is invertible, so we simply write it as the invertible operator plus what's left. Okay, we factor out the invertible operator. Okay, and now we argue that this is identity plus not compact, but upper triangular compact. Okay? So I'll show you in a second that the same analytic Fredholm theorem that holds for identity plus compact holds for identity plus upper triangular compact. And so we conclude that the spectrum is discrete. Okay. For the actual transmission eigenvalue problem, I'm cheating a little bit here, but the basic idea is once I know that b minus lambda naught I has a compact inverse, I can then treat this one, where now we have a different, this Im, remember, is not exactly the identity, but I'm going to treat this as a perturbation of that one. And this has the upper triangular compactness property. These upper triangular compact operators, just like compact operators, are basically an ideal. So if you multiply it by something bounded, you also have something that's upper triangular compact. And with a little bit of an argument that I'm not showing you, we also conclude that the spectrum of this guy is either discrete or all of C. And if you remember, I had I needed stronger hypotheses for the full problem. And those stronger hypotheses are really related to showing that that's not the case, to showing that there is at least one lambda naught where I can invert that. Okay. Okay. So what about the upper triangular analytic Fredholm theorem? Okay. So the analytic Fredholm theorem says that if you have a compact operator that depends holomorphically on Z in some domain, if you know that either, if you're looking at the identity plus that compact operator, if you know that the kernel is empty or the co-kernel is empty at some Z naught, then you know that the operator is in fact invertible at that Z naught, and in fact it's, what should I say? And that it's invertible at all but a discrete set of Z's. Okay. So if I have upper triangular compactness, I'm going to reduce that to identity plus a compact operator, and probably the easiest way to describe that is just do Gaussian elimination, but do it modulo compact operators. Okay? So simply different, here I've described it as an LU decomposition, but just multiply the top row by B and subtract. What you're left with is an identity plus compact. I think I'm going to spare you this. Okay, this is a verification that in fact the co-kernel of this is in fact empty, that there is a large positive lambda for which this is invertible. Okay, everything from here to here can be summarized in just multiply that equation by V, that equation by U. Do the 3 integration by parts you can do based on the boundary conditions. And you wind up with an identity that says, here's a negative real number, here's lambda is positive and real. This is the case where m is positive. So this number cannot be negative. Okay, so what we'll find is if u is non-zero, that has to be positive, that has to be negative. Therefore, the only conclusion is that u and v are 0. This picture here is discussing the coercivity assumption. Coercivity assumption says not that something is positive, but rather that for all values of x, its values always sit in an upper half plane. And if it sits in the correct half plane, it roughly says that even though various things can change sign, if you average it with a positive weight, it can't average to 0. So it's, in some sense, a relaxation of a positivity assumption. Okay, so last statement is just an example. So why can't I conclude anything about existence from this? And I'm going to just illustrate that by giving you an example. This example is due to Relic, I think in the 1940s. Okay. So I'm looking at the differential operator d dx. Okay, and I want to find its eigenvalues. So I try to invert d dx minus lambda u as f. And I'm going to show, and the boundary condition is u of 0 equals alpha times u of 1. Alpha is a real parameter. And so right here I've done the calculus, and I've written out for you the resolvent. Okay, so this is the solution of formula for u. F is always being integrated, so it's not hard to check that for any real value of alpha, this resolvent is compact. Okay. There's only one denominator. It's 1 minus alpha e to the minus lambda. Right? So the eigenvalues are the poles of the resolvent, and those are the places where e to the lambda is alpha, or lambda equals log alpha plus 2 pi I times an integer n. Okay. And right, for any alpha that's neither 0 nor infinity, I have an infinite family of eigenvalues, but as alpha goes to 0, they all run away to infinity. Okay? So another way to see that is when alpha is 0, this is the initial value problem. You have, okay, so the spectrum can run away. Okay? And in some sense, that's, so the Born approximation to the transmission eigenvalue, I can also put in such a family of things. I can put a boundary condition that says u restricted to the boundary is 0, and instead of du du on the boundary is 0, I'm going to put an alpha here and a 1 minus alpha and put a v here. Now, when in this case 0 is no, so 1 in this one corresponds to 0 in the previous slide. Okay. When alpha is 0, both u and v have Dirichlet conditions. This is not symmetric anymore, but it's close. And you can write down the resolvent, and you can show that the spectrum of that guy is just the Dirichlet spectrum, but it's all double. Okay. But in order to see that these eigenvalues still exist or prove any properties about them, the thing that has to be done is we have to somehow figure out, do they run away? Okay. Can they do what the previous example did? And at the moment, I don't know how to do that. Okay, and thank you for listening. Okay.
Questions or comments?
Just wonder, you said that upper triangular compact operators are basically an ideal. Obviously, they are not an ideal. Because if you multiply an arbitrary matrix 4 by 4.
You're right.
Okay.
I need to say something about I won't try to,
Okay.
I got it wrong once, I won't get it wrong a second time.
Okay.
Yes. They have, they're, right.
Any other comments or questions? Okay, if not, let's thank to the speaker again. Thank you very much.